Hello friends, welcome to this video. In this video we will discuss time period of pendulum. We will derive the equation for time period of pendulum and the differential equation for that. Okay, and these both things we are going to cover in this video lecture. So let us start. See, this is a pendulum. This is a rigid support with which the pendulum has been suspended. This is the pendulum. Suppose we take pendulum from here to here and we release it. So it will swing like this and then this. It will swing like this. So what we did, we actually uh, displaced it from its mean position and gave it some potential energy. So now it has energy stored in it. So when we release the pendulum, it it has this much energy that so when we release that, see, at this position there are forces acting on it. This is the tension of wire, and in this direction this is the tension of wire. Okay, and uh, and when uh, and one force want to bring it back to the mean position. That force is restoring force. So we will divide these. The see, this is mg. I have written in bracket. This is the energy stored in it, mg. Okay, so if we divide it in its two components, so one will be in this direction. So in this direction it will be mg sine theta, and in this direction it will be mg. So this is cancelled by this and this. These both are equal and are cancelled by each other, because so this is the tension force. But this one, yeah, restoring force want to bring it back, so it is this component. So the pendulum will move in this direction to the moon position, to the mean, towards the mean position. So when it moves toward it, what happens, the energy becomes zero at this position, but due to its momentum it overshoots this position and goes here. It goes past the mean position to here, and here once again what happens, energy becomes zero in at this position. No, sorry, energy, not energy, velocity at this position becomes zero, and energy is maximum. Again this the same happens. It's Energy is divided into two components, mg sine theta this one and mg cos theta this one. This one is cancelled by the tension of the rope, and it again swings back to the towards the mean position. Okay, this is the displacement x. So all this happens in this pendulum. Now we will first find out the differential equation. We will find out the differential equation for this. So we all know what is restoring force. Restoring force is F is equal to ma. But here you can see the restoring force that is acting is mg sine theta. Mg sine theta is acting. This is the restoring force that tends to bring this pendulum back to its mean position. So F is equal to mg sine theta. We all know force is equal to mass into acceleration. So I have substituted the value ma equal to, and mg sine theta is same. Now I will send this to that side of equal to. So ma minus mg sin theta is equal to 0. We all know acceleration is equal to d2x upon dt square. So m d2x upon dt square minus mg sin theta is equal to 0 is differential equation for this pendulum. Okay. Now we are finding the time period of pendulum. What we are finding? Time period of pendulum. So we will solve the first equation. Solving first equation, we will cancel out m. We get a equal to g sine theta. We all know that for small angles, theta equals to sine theta is equal to tan theta. Okay, so sine theta becomes theta. A equals to g theta, and a equals to g theta equal to x upon l. From where did we find out that? We know that theta is equal to length of arc upon radius. See, if this is the angle theta, so this is the length of arc, and length of arc here is displacement x. Okay, and radius is this one. This one is the radius for, will be the radius for this complete circle. So radius is l. Okay, so I will put theta equal to length of arc is x upon l. So this is the value of theta. I have put it here. Okay, a equal to minus g x upon l. First it was a equal to g theta, because for small angles theta equal to sine theta equal to tan theta, so a equal to j theta and a equal to g x upon l. This negative sign is for restoring force. Since the force was restoring, therefore I have put the negative sign here. So from here we get that acceleration is directly proportional to displacement. A is directly proportional to x, that is A is directly proportional to displacement. So what kind of motion it will be? It will be a SHM, and for SHM we have studied the time period. Time period equals to 2 pi under root displacement upon acceleration. Okay, so T equal to x upon A. Putting this value in this equation, putting this value, sorry, one second. So T equal to x upon A, from second equation, from this equation, x upon A equal to L upon G. ठीक है, x upon A is equal to L upon G. So put in above equation, we will put this value in this equation. So T equal to 2 pi under root L upon G. It should be T equal to 2 pi under root x upon A. So x upon A is equal to L upon G. So we will substitute the value T equal to 2 pi under root L upon G. Okay, I have forgot to write 2 pi here. It is like this, 2 pi under root x upon A. Okay, so I hope you have got this. Okay, so just keep watching, and this is the end of this video.